Hello again everyone, welcome back to ptet.chemistry channel. So this is an accompanying work 4 for the year 9, 14 to 16 years old curriculum. This is for the O-level 5070. It's also similar to the IGCSE, I forgot the subject code, but it's similar to the IGCSE chemistry extended, which is also similar to any 14 to 16 years old GCSE curriculum or whatever other curriculum that people are doing all around the world. This is an accompanying work for the associated lecture tutorials that I have covered, specifically on the ideas on when we work out mole, when we're trying to do volume of gases, that kind of thing. So without further ado, jumping straight onto the first question, we have an equation here. This is a fluorine molecule, group 7 fluorine molecule. The halogen exists as diatomic molecules where they form a single covalent bond. And then you have this giant ionic structure, Na plus OH minus. You also have this ionic compound with the giant ionic structure, Na plus F minus. You have simple molecule water and simple molecule oxygen, which is a double bond oxygen because group 6 element with 6 valence electrons, they would like to share with another non-metal atom two of the 6 valence electrons. So 6 plus 2 will give you 8 valence electrons around each of the oxygen. Anyway, this is about calculations instead of structure and bonding. We want to work out the maximum volume of oxygen. So we want this. And what do we have? We have the mole of sodium hydroxide. So we're going to compare the mole ratio. If I just start off with mole of O2, so we use the small n to represent, it means mole of oxygen, O2. I do this as a fraction. You have seen it in the example in the lecture tutorials. This is a ratio, is a fraction, something over something is a fraction, and does not matter really whether you put the oxygen on top or the NaOH on top, because it matters that one of it is the unknown and the other thing is the known. You must have one unknown and one known, then you can work out the unknown. But if you have got it the other way around, then you must follow whatever you have written down. Basically, follow your own answer. I have put down the mole of oxygen on top, so I need to see from the balance equation. This is a balance equation. There's 1 in front of O2, so it's just 1. This is from the balance equation. 1 mole of O2 is produced from 4 mole of NaOH. So this is to do with mole and mole. This is to do with mole and mole from the balance equation. That was why you have the balance equation correctly before you do mole calculation before this, all right? Now on the other side, on the right hand side, this is my favorite part of the bookkeeping. I leave everything on top for whatever I have written down here. Because of what I label, I follow what I'm doing. This one comes from here, from the balance equation. 4 comes from balance equation, equal to actual, what actually happened. What actually happened is 0.037 mole of sodium hydroxide react completely. So sodium hydroxide is NaOH. I gotta put the actual mole of sodium hydroxide, so it's 0.037. This is mole of sodium hydroxide that actually reacted, so this is the actual mole of O2 that get produced. The actual mole of O2, which is a gas by the way, so you know that mole of gas is equal to the volume of gas divided by the molar volume. The molar volume of a gas at room temperature and pressure is given in your periodic table, but you gotta know the value itself. This is 24 dN cubed per mole. This is molar volume of a gas at 25 degrees Celsius and 1 atmospheric pressure. So that's going to be the volume of O2. We want it in dm cube. You see this unit here is in dm cube, so this is going to be divided by 24, which is in dm cube per mole. So if you have the unit of gas in dm cube and then you have dm cube per mole, based on the lecture tutorial previously, this will give you the quantity with the unit mole of gas. So the volume of O2 there must be in dm cube because I use 24 dm cube per mole. So rearranging your equation, you should hopefully be able to see the math is I move up the 0.037. So there's 0.037 times 1 over 4. This is equal to volume of O2 divided by 24. Now what I can do is I can move the 24 up there. because it was divided by 24, so I do time 24. I could do all of that in one step, but that's because I've shown you what I intended. If you couldn't see the math, I would encourage you to do it step by step until you could see it. If you couldn't see it, do not try and take a shortcut. I didn't put a unit there because I already have the units matching. So there's a bit of corrections to make with regards to these questions. They say give your answer to two significant figure. So I actually missed that the first time when I read through the question. So two sig fig would mean that this is our first significant figure, second significant figure, and this is our third significant figure. They want up to 2 sig fig, so we look at the third one. This is lesser than 5, so we don't add anything onto that, which means the final answer to 2 significant figure would just be 0.22 dm cube. Alright, and I spotted another mistake as well in the latter part of the question, so they'll be appended in the question 4 as well. On to question 2. So this is a reaction of sodium with water. So this is your metal. This is your reactive metal. Metal plus water give you metal hydroxide and also hydrogen. I told you previously in the lecture tutorials, many lecture tutorials ago, there are a couple of equations that you got to know based on the general chemistry. Metal plus water give you the alkaline metal hydroxide and the hydrogen gas. You do not get salt because we don't have acid here. Now we need the mass of sodium. We need it in gram. So we need the mass of sodium, we need it in gram. We are producing 300 cm cube. Do not forget that 1 dm cube equal to 1000 cm cube. So be aware of that because the hydrogen is a gas. The H2 is a gas at room temperature and pressure. Is a H2 gas. So the molar volume of the gas is going to be 24 dm cube per mole of the gas. And we're going to give our answers to 3 significant figure, and we'll worry about it when the time comes. Let's set up our mole ratio. So as far as we know the volume of hydrogen, and we have the molar volume, which we can use 24,000 dm cube per mole, because we are given the volume in cm cube, and I know dm cube is equal to 1000 cm cube, so I can multiply that by 1000 to give me the molar volume at room temperature and pressure as 24,000. Oops, I have done that incorrectly. That shouldn't be dm cube, that should be now cm cube per mole. Okay, so now I have this information. I want the mass of sodium. That's what they says, sodium. So if I have the mole of sodium over the mole of H2, one of which is known, one of which is unknown. So I'm going to equal that to the ratio in the balance equation. I've decided to put the sodium on top, so I follow there is 2 sodium and there is 1 hydrogen. On the top, there is 2 mole of sodium over 1 mole of hydrogen from the balance equation. Balance equation. On the other side, this will be the actual. This is from balance equation, theoretical. This is what actually happened. I have the mole of gas. The mole of gas is going to be the volume of gas divided by the molar volume, the unit of which must be the same in order for the unit to cancel out. So there is cm cube divided by 24,000 cm cube per mole. So notice that I've decided to put a unit in there so that you could see and not divide by 24, because 24 is 24 dm cube per mole, and you got to be very careful about your units, which is basically maths. Okay, on the top there you want the mass of sodium, but you know that it means the mole of sodium, and you want the mass of sodium. So you know that mole of sodium equal to mass of sodium over the relative atomic mass from the periodic table, which is 23. So what we can do is we can do mass of sodium in gram divided by 23 gram per mole. Gram over gram per mole give me the mole of the solid sodium. So what I can do now is I can move this up. Then I will have mass of sodium over 23. So there's 2 times 300 over 24,000. Of course, then I could have done the 23 move up in the same step, but I just want you to see it stepwise. So I can move up the 23 This is divided by 23. So when I move up the 23, it becomes multiplied by 23. Before I come up to the final thing on my calculator, I would always try and rearrange everything first before I put everything into my calculator and get my final answer. So I get my final answer as 0.575. That is not good enough of an answer because this is the mass. The mass was previously given in gram, because gram over gram per mole will give you mole. cm cube over cm cube per mole will give you mole. So you know this is in gram. This is in gram, and they want it to 3 significant figure. 1, 2, and 3. This is not counted because this is in front of the first number, which is not 0. So this is 0.575, 1, 2, and 3. So there's 3 significant figure. Okay. Moving on to the next question. So we have calcium carbonate plus hydrochloric acid give you salt. So carbonate, metal carbonate plus acid. In case you forget, you should always go back to your a simple general word equation. Metal carbonate plus acid will give you metal salt. The salt you get from hydrochloric acid is obviously a chloride salt. The metal is calcium, so you get calcium chloride, Ca2 plus, Cl minus. So I hope you know that charges have to cancel out. You must have 2 of that, and you must have 1 of that in terms of the transfer of electrons from one group 2 atom loses 2 electrons, 1 to each of the group 7 element, group 7 atom in order to gain 1 electron each. So you need 2 of them. Okay, so everything makes sense in terms of structure and bonding. This is carbon dioxide. Carbon dioxide consists of a double bonded oxygen to carbon, and the carbon form 1, 2, 3, 4 covalent bond because carbon is group 4 element. 4 share with another 4 electrons, 2 from each of the oxygen. Altogether 4 plus 4 give you 8 electrons around the carbon. From this kind of display formula, you should be able to draw the dot and cross, where of course dot cross, cross, dot, oxygen. And that is number 1 mistake by a lot of students, because when they ask you to draw the outer shell electrons, you can see the oxygen is not happy with just 4 electrons. In fact, oxygen is from group 6. So oxygen originally has 6 outer shell electrons with the 6 dot I've shown there. And of course, it now shares 2 electrons. 6 plus 2 is 8. 6 plus 2 is 8. 4 plus 4 is 8. So they're nice and happy. Water needs no introduction, so you know it's that. Of course, you can draw the dot and cross if you want to as well. My focus on this question, however, is on calculation. So they want the mass of calcium carbonate, which is this thing, and you are producing this much volume of carbon dioxide. Carbon dioxide is a gas at room temperature and pressure. In fact, if you are living right now, you are breathing out carbon dioxide because you are doing respiration. You are breathing out carbon dioxide and you are breathing in oxygen as part of your body function. So I have these. I don't know this. Okay. So incidentally, you can hopefully see that again. They want you to do it 3 sig fig. Hopefully, you can see that the mole of calcium carbonate over the mole of CO2 is just 1:1. 1 mole of it is to 1 mole of it from the balance equation. If I do equal, on the top I have solid because they want the mass. So I have mass of calcium carbonate divided by the MR. So I should really work out my MR of calcium carbonate on the side, and I have to show my working. 40 times 1 plus 12 times 1 plus 16 times 3. Put it onto your calculator and you will get 100. And I've done calcium carbonate a lot of times to know that it will give me 100. Okay, so mass over MR, mass in gram over the MR in gram per mole. This will give me the actual mole of calcium carbonate that reacted that is needed to produce however much volume of gas. So in terms of the volume of gas, I'm given cm cube. So there is 16.8 cm cube. Therefore, I need to divide it by the molar volume in cm cube per mole. So this is going to be 24,000. So you learn there are 2 variants of molar volume of gas. Of course, the one given in your periodic table is 24 dm cube for 1 mole, because 1 mole of any gas occupies volume. 1 mole of any gas occupies a volume of 24 dm cube at room temperature and pressure, and that is equal to 24,000 cm cube per mole, because 1 dm cube equal to 1000 cm cube. 1 dm cube equal to 1000 cm cube, and that is a conversion unit that you have to remember, especially when we come to solution chemistry, when we also deal with 1 dm cube quite a lot. So that is cm cube per mole. I don't write down the unit, but this is gram and this gram per mole. This cm cube divided by the molar volume. This will give you the actual mole of CO2 produced. That comes from the actual mole of calcium carbonate that is needed to produce however much that is. This is 1 and 1, so I can move this up there, and hopefully you can see that after I rearrange everything, I'll get 16.8 over 24,000 times 100, because I've just moved this up there and then equal to that, and then move the 100 up there, so it becomes multiplied by 100. So you can do it step by step if you couldn't see what is going on. On my calculator, it shows 0.07, and this is 0.07, so this is only one significant figure, because this number in front is not considered a significant figure. So this is the first, and this is one significant figure. They want 3 significant figure. They were very kind to bold it for you, so you shouldn't have made any mistake at all. And this is mass of calcium carbonate in gram, because of how we define it as gram over gram per mole. So that's 0.0700 to 3 significant figure, 1, 2, and 3. The number in front do not count because they are 0 before the first non-zero whole number. Question 4 is further, well, it is an ammonium iodide. Ammonium iodide is a giant ionic structure. It consists of ammonium ion and iodide ion, which of course you could do qualitative analysis tests. With sodium hydroxide, you heat it, you get ammonia gas, which will turn red litmus paper blue because you get ammonia gas. This thing you can test with silver nitrate. After you acidify with nitric acid, then you add silver nitrate, and it will give you a yellow precipitate of silver 1 iodide, Ag plus I minus, which is insoluble. All the silver chloride, silver bromide, silver iodide are insoluble. The silver iodide is yellow in color. You will have seen it in the qualitative analysis that you have done in the lab. So when you heat it, so you're just heating it, it will decompose to give you ammonia and HI. So this is actually a base, or we call it alkali. This is an acid. This is actually a salt. When you react an acid and a base, you will get the salt, but when you heat the salt, you get back the base and the acid. Now, what do they want you to do? They want you to calculate the volume of gas measured at room temperature and pressure. So we can use molar volume of gas, which is 24 dm cube per mole. But don't forget, they didn't write the units. They didn't tell us what's the unit. They didn't write down the unit there. So we could also be using 24,000 cm cube per mole, depending on how big the answer or how small the answer is. They have given us the mass of ammonium iodide. So I have this, I don't have this. So I have one unknown. So the mole of ammonia is to the mole of NH4I is 1 over 1. On the top there is for the mole of ammonia from the balance equation. At the bottom there is from the balance equation, 1 mole is to 1 mole. These are from the balance equation is equal to what happened in reality. In reality, the gas is ammonia. The gas is ammonia. So I will have the volume of ammonia, which is a gas. I will say that it is in dm cube. If I say this is in dm cube, then I have to use divide by 24 dm cube per mole, because if you could follow the units never lie to you. Unless you do not write down the unit, then it will lie to you. Be very careful about that. At the bottom, I have ammonium iodide. I am given the mass. This is mass. If I'm given the mass, I need to think about MR. The MR of NH4I is going to be 14 times 1 plus 4 times 1 plus, you should show all your working anyway, because they're actually part of the reason why it's 3 marks, because you could get 1 mark just by showing the working to calculate the MR correctly. So the relative atomic mass of iodine is 127, group 7 all the way down there, element 53, 127 is one of it, 4 hydrogens and 1 nitrogen. So I get that to be 145. So at the bottom there's the mass of the solid, mass over mR, 2.90 gram divided by 145 gram per mole. So at this early stage, you'll see that I write down the units a lot so that you're not confused. But when you get to a more advanced stage later on, you would have these things ingrained in your mind that hopefully you won't make the mistake. But one mistake, remember, one mistake with the units, then all your answer become wrong. Okay, so I'm writing this down so that you could see it and you could practice by looking at it so many times they become natural to you. But unless you become natural with it, stick with it until you become natural, then you can start omitting them. All right, so the gram, so it will give you mole of NH3, the actual mole of NH3 that comes from the actual mole of NH4i that decompose. So because it is 1 and 1, so I could just bring it up there, and then I'll get volume of NH3. This is in dm cube, by the way. Okay. Yes, I know I've talked about cancellation, but this volume will still be in dm cube based on how I define it in my original equation as shown very, very clearly there. So nothing has been lied to you. Everything is very clearly set out to you. Bring this up and then bring the 24 up. Do it in 2 steps if you can't see it, but you gotta be able to see it in order to progress further in chemistry actually. So this is 0.48 dm cube. You could leave your answer like this, so it's not such a small number. If you want, you can multiply by 1,000. So 1 dm cube is equal to 1,000 cm cube. So you could multiply by 1,000 and you will get 480 cm cube. So either of the answer would have been alright. If you write down 0.48, that is wrong. 0.48 dm cube, that is correct. If you write down 480, that is wrong. If you write down 480 cm cube, that is correct. They haven't put down any units there, unlike the earlier question. So you could put either of these down unless they have specified what units they want it to be in. So there's another mistake which I had done with this question 4, and that is because it says they want the volume of gas, of which I not only have this as a gas, but I also have the HI as a gas as well. So it's very important that we don't miss out that there's another gas being produced. So instead of having it as the mole of ammonia, I could also express it in another expression, so where the mole of HI is to the mole of ammonium iodide is equal to 1 over 1 is equal to volume of HI over 24 in dm cube. And then I could do the same thing, 2.90 over 145. Of course, then I could work out the volume of HI in dm cube. Then there will be HI gas in dm cube. This will be NH3 gas in dm cube. I can add up their volume. But I can see that it's going to be the exact same volume, but this is the volume of NH3, and the volume of HI will be another 480 cm cube or 0.48 dm cube, which means the total volume of gas will not just be the NH3, it will not just be the HI, but it's the combination of the volume of the gas number 1 and the volume of the gas number 2. So it's really up to you how you're going to do it, I guess. The volume of HI is also going to be 0.48 dm cube, which is equal to 480 cm cube. So that is just one way of doing it, where you do them individually like this. I'll now show you another way of doing it, which is just to combine mole ratio. So instead of doing it individually like this, what I could have done is I could have, instead of NH3, if I change that to gas, now I'm going to change this to gas. So the mole of the gas is to the mole of the NH4i is no longer 1 because I have 2 moles of gases, because this is a gas and this is a gas. 1 mole gas, another mole gas. So 2 mole of gas is to 1. And I will not have volume of NH3 anymore. I'll have volume of gas. This is the total volume of gas divided by 24 dm cube per mole, because whether it's this gas or this gas, they both occupy 24 dm cube for 1 mole of a gas. That is the definition of molar volume. And that is related to, using up 2.90 gram of this ammonium iodide. So instead of NH3 there now is my volume of gas. And then that will be multiplied by 2, because when I bring this up, and then it will be 2 over 1. So I'm missing something. I am missing a bit of space down there. Let me see if I can find a bit more space there. So I'm just going to move there on that side. So I have 2 over 1 multiplied by 2.90 over 145 multiplied by 24. So altogether I will not get 0.48. Instead what I'll get is 0.96 dm cube, which is equivalent to 960 cm cube, because this is the total volume of gases from 1 mole of NH3 and 1 mole of HI, whereas previously I just shown you the mole of ammonia separately, and here is the mole of HI separately. So I can just erase these now, because now what I've done is I have combined the mole of gases into my expression, where this is mole of gases actually, because there are 2 gases related or related to the mole of the ammonium iodide. So yeah, there was a reason why I had to well, kind of like re-upload another tutorial video to replace this older one in order to add in this very important information. Question 5. So you have done this in one of the practical classes. I've shown you hydrogen peroxide. Hydrogen peroxide is H2O2. It can decompose to give you H2O and O2. We can balance this equation because 2 oxygen, 3 oxygen. So I need 2 of that and 2 of that. Now 4 hydrogen and then 4 oxygen. 2 oxygen plus 2 oxygen give me 4 oxygen. This is a liquid. Colorless liquid, it gives you colorless liquid water, and it gives you this gas O2. It's very slow on its own. What you do is you do MnO2 catalysis. This is called manganese 4 oxide. So it's Mn4 plus and O2 minus. So I hope you haven't forgotten anything about balancing equation. We bring down the charges and we think about the value. The value is 2 there. The value is 4. But we want the simplest whole number ratio. Simplest whole number ratio. So you could divide by 2 and you will get 1:2. So this means 1 Mn4 plus, and then you have O2 minus and O2 minus. That's why the formula is MnO2. You will learn more about why MnO2 will make good catalyst when you come to transition metals, but just for the sake of it, this is a black color solid. And if ever you encounter this in qualitative analysis in exam, you add a little bit of this black solid to this, and then suddenly you get effervescence. The gas is colorless, the gas is odorless, it doesn't smell anything. You can test for it by using a glowing splint. A glowing splint is not where the fire is still burning, it's where you get a flicker. A flicker meaning the fire is already gone, it's no longer burning, but there's a little bit of the flicker of the flame, and then when you put it into the tube that contains oxygen, the glowing splint will relight. It will relight, meaning it will go back into burning. Or sometimes we call that rekindle. Rekindle meaning it lights up again, it relights. This is a graph. You must learn how to read graph. This is the volume of oxygen produced within the time. At time 0, at the start of the experiment, there's no oxygen produced. As time increases, more and more oxygen get produced. But then here, no more oxygen get produced. The maximum volume is 60 cm cube, and no more oxygen is getting produced because perhaps there's no more H2O2 to decompose. Basically, the reaction has finished. All the H2O2 has gone into H2 and O2. The reaction has finished. And once the reaction has finished, there's no more oxygen being produced. Oxygen is a product. When there's no more oxygen being produced, that's because no more of the reactant reacted. Okay. So what do we have? We have the mass. Careful. We have the mass of manganese 4 oxide. But if you look at this equation, manganese 4 oxide is not in the equation. When I say not in the equation, I mean it's only a catalyst. It is not involved, it's not used up. See, this bit doesn't have manganese, this bit doesn't have manganese, this bit doesn't have manganese. The oxygen from here doesn't come from manganese oxide, it comes from H2O2. In fact, a catalyst is never used up if you get the exact same amount of catalyst at the end of the reaction. So this mass there is no use. Okay, no use of you trying to work out the MR of MnO2 because it's a catalyst. All right. On the other hand, the volume of O2 is going to be important. So 60 cm³ of O2 get produced, and you use 50.0 cm³ of aqueous hydrogen peroxide. Okay. So after how many seconds? After how many seconds did the decomposition finish? So basically, when does the reaction complete? Complete reaction. When the oxygen is no longer being produced because no more products, no more oxygen, that's when H2O2 finish reacting. When does it finish reacting? Here you could see it's getting slower and slower and slower. There is still a bit of oxygen being produced because it hasn't reached the 60 yet, and just about there where I mark it green there, that's about when it level off, because here it's still increasing, here level off. So we need to read the graph. So it's there. This is 30, this is 40. It stops there, which is halfway there in between. So that's between 30 and 40 exactly. So that's 10 squares, so that must be 35 seconds. So 35 seconds. This is the SI unit. SI unit for time. This is SI unit for second. You have learned that in physics. Now, how many moles of oxygen were produced at the end of decomposition? What is the total volume of oxygen produced? The total volume of oxygen produced is 60 what? 60 cm³. So learn to read very carefully. So part 2, the mole of oxygen will be 60 cm³ divided by, this is 24,000 cm³ for 1 mole. This is what you call the molar volume of gas at room temperature and pressure, 25 degrees Celsius and 1 atm. So 24,000 cm³ per mole. I've talked about this again and again and again. So 60 divided by 24,000, that give me 2.5 times 10 to the minus 3. This is what you call standard form, where the number is bigger than 1 but it's lesser than 10. So that is mole. Okay, they want how many moles of oxygen. Now use your answer to 2 to calculate the concentration in mole per dm³ of the 50 cm³ aqueous hydrogen peroxide. This is aqueous, this is concentration. How many mole of H2O2 in 1 dm³ of water? So from our equation, you can hopefully see if I go up. From our equation, the oxygen is 1 mole. So 1 mole of oxygen comes from 2 mole of H2O2. So you want the concentration of H2O2, and you have this. You have the volume, you have the mole, you want the volume, you want the concentration of H2O2. So 2 H2O2 give me 1O2. 2 H2O2 give me 1O2. So 2 H2O2 give me 1O2. 2 H2O2 give me 1O2. That is from the balance equation. From the top, I have solution. This is called solution. It's the next part of the topic. When you have mole per dm³, you multiply by the volume of solution in dm³. Concentration in mole per dm³ times dm³ is going to give you mole of the solution. So you have the concentration of H2O2 in mole per dm³ times 50.0 over 1000. This is dm³ now because I divide by 1000, times mole per dm³ will give me the actual mole of H2O2 that reacted. This is the actual mole of O2 that gets produced, so that's 2.5 times 10 to the minus 3. So altogether, concentration of H2O2 is going to be 2 times 2.5 times 10 to the minus 3 divided by 50.0 times 10 to the minus 3. So where does that 10 to the minus 3 come from? Anything divided by 1000, anything divided by 1000 means 50.0 times 10 to the minus 3. This brings up, this comes down, therefore it's divided by 50.0 times 10 to the minus 3. So now pop that into your calculator. 2 times 2.5 times 10 to the minus 3 divided by 50 times 10 to the minus 3. I get the answer to be exactly 0.1 mole per dm³, because this was in mole per dm³ times dm³ give me the mole, the actual mole of H2O to the reactant. Now, this is one significant figure. If you look at the answer here, this was two significant figure. This was 1, 2, and 3 significant figure. I would be hesitant to just leave it to one significant figure. This is a skill you will learn more in practical. It's called appropriate. This is your decision making based on the data. The data given here is 3 sigfig, 1, 2, and 3. The data you have used is 1 and 2. You should do 2 or 3 sigfig. That will have been alright. I would just leave it to 3 sigfig because it's to a greater accuracy based on the volume of the aqueous hydrogen peroxide used. And then I'll just quickly write down 3 significant figure just to show the level of accuracy I have worked to so that the examiner know what I'm talking about. Alright, so that's it for this lecture tutorials. This is basically a lecture tutorial on work 4, which is largely to do with the volume and the mole of gases, although this last question has to do with concentration of solution, which we'll move on to, we will have already moved on to in the lecture tutorials, but the work of which will be covered a lot more in detail in the next work 5. So thank you for watching, and don't forget to click the button on the bottom right to subscribe to the channel, and do share the channel widely with all your friends, chat crew, juniors and seniors from school, relative, and whoever else you think the channel might be useful for. So follow me at ptet.chemistry, ptet.chemistry on Facebook, Instagram, and Twitter to get connected. Thank you for watching again.